Oh, welcome to PyData's Boston's February 2021 meetup. I'm glad to see so many people interested in these subjects. Our topics tonight will be geodata processing and vocating, turnout, and I'll skip around because we did some of the stuff out of place, like Q&A.
You want to share the slides?
Sorry about that. Sorry.
No, all good.
Okay. Share screen. Okay, is it the share screen option?
Yep.
Yeah, that should do it.
Also, okay, cool. Are you guys seeing the PyData slides?
Yes.
Yep.
Awesome. All right. Since you guys already introduced yourself, I'll jump to the second item. You guys are cool to ask questions at any time. Please turn off your microphone when speaking. Here are different sites and meetup links. Please feel free to join, sign up, retweet, and of course, reshare on your own platforms if you're on Facebook or some obscure thing we don't have on here yet. Would definitely be much appreciated. Okay, why is this thing not going to the next thing? Okay. 1 second, a little bit of lag on my part. So anyways, PyData Boston is a member of the PyData network, who are a sub-project of the NumFOCUS organization, whose code of conduct we all fall under, and we take serious inclusivity and non-discrimination, like things like racism and sexism, horrible no-nos we will not tolerate. We want to be a friendly, inclusive environment. And volunteers are also always needed for organizing going forward. As you can see, the online part is the main relevant one. And we will, if Cesar's ready to go, we'll move on to him. You ready, Cesar? All right.
Yes, I am.
All right, should I just make you a co-host?
I think so.
All right.
Set host as disabled participant screen sharing. Maybe you need to stop sharing.
All right. All right, there it is. All right, you're the center of focus, Cesar.
All right, can you guys see my screen?
Yes,
Yep.
Cesar, I can see you. I can see and hear you fine.
Awesome, great. Yeah, super excited to be here tonight presenting about this. This is a project that I worked a lot on last year and a little bit this year as well. I wanted to introduce myself a little bit. So my name is Cesar Hernandez, and I've been working with data maybe for the last 10 years. When I started working in data, I was at Deloitte, working with a lot of financial data. And then I moved to Vistaprint 2014, where I was working in the CRM team and also in the data science team. And in 2017, I moved to TripAdvisor, working in product analytics, where working so many different projects. But eventually, I sort of like started working mostly on data engineering projects. Most recently, I'm working with the machine learning team. Yeah, and also one of my hobbies is hiking, and I enjoy hiking in winter. So you can see here that during all this COVID pandemic, I actually grew my beard, and this is how my beard looks when it's frozen. Yeah, so today I want to talk to you about a project that I work on, that I volunteer my time to work for. Is something that we named Crowd-Free. For those of you that don't know what Crowd-Free is, it's basically something that basically gives you some ideas of where, how like crowded is different places are in a given place. So funny story to provide some context. So in February last year, when all COVID started, we had a hackathon. One of the idea was exactly this, was basically, sort of like the main use case was like, hey, I need to do groceries, but I basically sort of like completely quarantine at home, but I need to go to the grocery. How do I know where to go? During that hackathon, we started working with different libraries, and we got to do something pretty cool. But I realized that in order for me to actually be able to put something like this together, I needed like more help. I'm not a front-end engineer. I do a lot of data stuff, but not necessarily front-end stuff. And at the same time, I realized there was a group at TripAdvisor, which is the company where I work on, that was actually trying to do this. And they actually needed somebody that could work with data. And I was like, oh, okay, sweet. I can sort of like try to bring the help to bring this idea online, and also at the same time learning a lot about like geodata, because in my regular job, I actually don't work with any geodata. I work with a lot of web data, but not necessarily geodata. For those of you that have worked with geodata, you probably know that it's quite complex, and I'll explain why in a second. So the main app is basically just looks like this that is on my screen right now. It's a big map. We have the entire United States, and you can like search for a place. You can move. You can see like densities in different hours of the day for different places. If you click somewhere, you can actually get a histogram of like how crowded a specific place is, and you can also get some information about that place. It's quite simple. In the back end, there is a lot of data processing, and that's what I want to talk to you about today. So at the one thing that we do with Crowd-Free is that basically what we are doing basically is getting data from cell phone data, and then we aggregate all that data, and then we try to show that to the user in a way that is easy to understand, so people can make their own decisions about where to go. When we started the project, sort of like our sketch looks a little bit like this. It was something, this is what we thought that it was gonna be. And at the end of the project, this is what it was. Almost everything on the bottom of this diagram is all data processing. And then almost everything at the top of this is the front-end application. The same way that we did a lot of different iterations, we also iterated a lot with the visualization. So in the beginning, it looked something like this on the top right. And then we actually got some cool maps with heat maps to work. And then finally, we got to what it is today, that it looks like this. So I'm gonna get to work to talk a little bit about the data. The data that we are using, there are basically three different kind of like ingress data sets that we consume. The first one is places, or that we call places, and this actually was donated by SafeGraph, which is a company that works with geodata. And what they provide to us is every month they provide a huge file that contains all the businesses in the United States, and it contains the polygon information. and I'll get into what the polygon is. But in addition to that data, they provide other metadata that is quite important about the business, like hours of operations, the category of the place, the address that is important, and a lot of other different data. The other data set that we consume is open spaces. So open spaces is coming from OpenStreetMaps. This is an open source data that anybody could get. It basically gives you parks information and open spaces information. So if you, for instance, want the polygon that defines what the Boston Common is, you can actually get it from this data set. As I said before, places provide only businesses, but we thought that one of the cool use cases for this was like, we all need to recreate and go outside, and we necessarily don't want to go to businesses, and maybe we want to go to a park. But if we're going to a park, like which park do you go? In what place of the park you want to enjoy some time outside? So this is one of the other data sources that we consume. And finally, the data that is the massive data that we receive is the telemetry data. And the telemetry data is actually provided by two companies, XMode and Betaset. And what this data is basically your cell phone, depending on the apps that you have, is capturing a lot of your signals of your cell phone. And then these companies aggregate this from multiple different, multiple apps, and they sell this data to other companies. This is how they do like marketing. And in the case of this application, this data was also donated to us. And we receive this data every day, and they give us an update that expand to between 24 and 48 hours. So what does the polygon data looks like? So the polygon data looks like just like this. So this is like one of the records that we received. The polygon data is basically a bunch of different points that can basically define the contour of a given place. So if you had like a square, you basically just need 4 points, but most polygons data is very, very complex. And this polygon WKT, that is a well-known text representation of geometry, might be massive. As I said before, like, so this is quite important because this basically defines the space of a business. As for the telemetry data, we get roughly 5 billion records every day, and the data is quite rich, but the data, as well as rich, is very duplicated. So depending on the cell phone device that you have or the app that you have, your cell phone might be capturing up to 1,000 different signals every single day, even if you just have it, you know, on your desk. And the data is really rich. So we have stuff like advertiser ID that sort of like define your cell phone, but it contains some of the most important stuff, which is latitude and longitude that give us sort of like the exact location of a given place. And something else that is quite important to our model is a speed. And I explain why speed is important as well. So the sort of like the summary of what we really wanted to do was to do something like this. Imagine that you have this place in here that is defined with the polygon, and you have all these different points that define where people are in a given hour. So with the polygon, you can actually get the area of the place, and given all the points that are inside, you can actually come up with a score that is the density of that place on a given hour. So in this case, if we have exactly the same place, and we have hour 10 and hour 11, on hour 10, we have 6 different signals that were inside the polygon. And on hour 11, we have 4 different signals. So that tells us that for that specific polygon, relative to itself, we know that it's more dense at like 10 a.m. than at 11 a.m. So one of the reasons why we do density is because the polygon can be really big. So it's not the same to have 100 people in a really big place, like let's say Home Depot, that if you have 100 people in a tool store that is small. So we basically try to normalize by the area. So that way people can make informed decisions about where to go depending on how crowded a place is. In the same way, something that we do for normalization is that we also normalize depending on the zip code. So that way people can compare the similar places or around the place where they live. So if we don't do this, we get into a place where everything in New York, for instance, is gonna look crowded, and everything in a place, in a rural area is not gonna look crowded. The main use case is for people to use this locally, to be like, oh, I need to go to the pharmacy, or I need to do groceries, or I want to go to a park. So we want to normalize by the area where they live. So that way, when people are like searching, they can actually compare places around their locality in an easy way. All right, so for open spaces, sort of like the process is a little bit different. So imagine that we have something that is huge, right? Like let's imagine like Central Park in New York. If you try to come up with a density for Central Park, it's gonna look quite low, because in reality, there are only few places, especially like the roads that cross the Central Park, that is where people are located. So something that we did is to use a library that was created by Uber, and it's open source. It's called H3, and there is a Python API that you can use. And what it gives you is a hex representation of the world. So why hexes is because like it's a really good compromise between circles and squares, and they're not gonna overlap with each other. So in this case, you can see here that, I don't remember the resolution of this photo, but I added in here a link so people can actually find some examples of this. You can actually get different hexes in here. So imagine that you have Central Park in New York. You can actually get different hexes for the entire Central Park, and then try to calculate the density on those hexes. Once that you have these hexes, you basically can treat this the same way that we treat the places, which is basically just, well, I have the polygon information, and then I'm just trying to calculate the density in there. So I want to give you an example of what this looks like. So this is what it looks like for Waltham Square. So I used to live in Waltham, so I know this place pretty well. So you can see in here, like everything in here that looks like a polygon, where you can actually see the shape of the polygon really well. This is a business or a place that we get from the places place. But in here, we know that this is actually, it's coming from the open space. And the only reason I know that it's open space is, well, one, because it's a park that I know. And second is because the representation of the data is a little bit different. So you can see in here that we're using heat map. So that way, if I actually want to go to the park, I can actually tell that, okay, on this area in here on the top right of the park, there is usually a lot of more people at this time of the day on Wednesday. And then I can decide to go with my family to another place. The way that we visualize the data is a little bit different as well. We use heat maps as well, instead of like hexes, because we just didn't want to show all the polygons on top of the different places. So if I go back in here, this is how one of the visualizations early in the process of how we were like trying to visualize this. It looked a little bit like this, and it's kind of crowded. So we ended up using heat maps instead of like hexes. All right, for the fun part. So I just want to explain. So now that you have some of the context of the data, I just want to give you an idea of the scale of the data. So I mentioned that we have around 5 billion records for all the signal data. And again, these are points of data at different times of the day. And for the polygon information, we have around 4.1 million records from SafeGraph and about 2 million records from OpenSpace. So one thing that, as I explained before, we had a bunch of partners. One of those partners was Amazon. And they allowed us to use their entire infrastructure. So there is this database called AWS Athena which is pretty cool because what you have, all your metadata is saved in S3, and then you basically build your entire data set database on top of S3. And the engine that Athena uses is similar to Presto. So that way you can actually use pretty cool functions that are created in Presto. And the library for geo functions is quite comprehensive. One of those is stcontain, which if you see here, you can basically pass two geometries and it's gonna return true or false if the geometry on the right is contained on the geometry on the left. So one example in here, in this case, you have this geometry, and this is actually a square. If you see here, there are 4 points that define a square, and you have this point 0, 0. So in this case, I'm not sure, but it basically is gonna give me like, oh, this point is in this square or it's not. However, when what we're doing, so there are like quite big limitations in here. So one is the scale of the data. So if we're talking about 5 billion records for signals and 6 million records for polygons, in order to apply this, it's basically a cross join of data. And once that you join this, it's just massive. It's really, really big. So that's already that was already a limitation that we hit early on. The second limitation is that geo functions are very computing expensive. So if you try to do this operation, you pretty much are like, no matter the database, even AWS Athena with like trying to expand the limit of all your computing power, this is gonna fail. So we had to come up with different ways to do this. So one of the first things that we thought about doing was just to partition the data. So since we have 24 hours of data on a day, we thought, well, let's just break these 5 billion records and then just try to process 1 hour of the time. So that way we can actually, maybe this works, and that didn't work. So we had to do something else. So for that, we basically use H3 again. So something that is really cool about H3 is that it allows you to get a mapping, an index for a given location. So in this case, you can see here that if I pass to H3 a latitude and longitude and a resolution, and the resolution is basically how big your hex is. So something like, right now I'm just guessing, but maybe resolution 0 might be just a massive hex that covers the entire wall. And the bigger the resolution is, the smaller those hexes are. So if you put something like this, latitude this, longitude this, you basically get something like this. It's just a string that you can use. If you pass a polygon, in the case of Walton Square, and this is the actual polygon information, you get an array of different hexes. So why is this important? It's because now your join doesn't really depend on geo functions that you need to apply to the data. Now, if I basically explode this array, I can actually do just an inner join with this data set. And that has like a massive, massive improvement, and it actually made our life, made the project possible to do. And not only that, is the other thing is that as you are doing this inner join, you're also filtering data. So one thing that we wanted to do is to make sure that we were not showing density of people houses. So we wanted to make sure like, oh, we're selecting just businesses. So once that you do an inner join of pre-selected data, you can actually just get rid of anything that is not a business or a park. The other thing that we did is to dedupe the data. So as I said before, I mentioned that your signals, your cell phone might be capturing a bunch of different signals. So, and if you, in this representation here, if we have two signals on the same hour, on the same hex, we know it's only one person. So we don't want to, like show that display is super dense just because some cell phones are just taking recording many more signals. So because we have the advertiser IDs, we were able to dedupe the data. So that way something like this at the end will look a little just like this. So for these two So this dot in here, the green one, is just the same device. It will just look like one. And I mentioned before, another thing that is important is the speed. So if you think about like, well, Central Park in New York or even Boston Common, there are some like car roads that traverse the park. So the first time that we sort of like visualize this data, you will see a ton of people in the roads, but these were basically just cars like driving, and we didn't want to show this. So with the speed, we were actually able to filter anything that was moving like faster than 3 miles per hour. So that way we were making sure that, or not making sure, but trying to reduce the chances that the signals that we were capturing were from moving vehicles in the place. So once that you basically have the hexes, the join is much simpler, right? Because you sort of like reduce the space where you need to apply the geographical functions. So in the example that I was giving before, in my end, that you have all these points you have an index, and then you join to the Walton Square. So you first have like a first pass where you join that, and then you can apply the geo function to make sure that the points are actually inside that polygon. The other thing that we did is basically we parallelized the way that we were querying all the data. So we split all the data. So the data was coming to us already partitioned by hour. So it was quite easy just to parallelize the process. So every hour was running independent to each other. And that way, the final result was almost an aggregation at the hour level and at the business level. For everything that we did, we basically used Airflow. And this was my first time using Airflow because in my TripAdvisor, we actually use something that we built in-house that allows you to do pretty much the same, but the way that you interact with that is a little bit different, but sort of like the concept of how to build a pipelines are the same. You know, you have dependencies, this can only run whenever this is done. There are parallel tasks, and this is only one of the 6 different ETLs that we have running for this project, which is one of the more complex. And we're using Airflow with Boto3, so that way we can interact with all the Amazon services that we use. And that way we can actually come up with the final representation of all the data before we actually send it to Mapbox, which is one of the other partners that actually is able to render the map on the site. Finally, like some of the technologies that we use. So we have a few EC2 instances. So each one of these is actually running Airflow. So we have backup of the data, of the process. We're using a Spark EMR. Something that I didn't mention about why H3 is very important in the way that it works is that it's basically, it's a mapping operation. So it's basically, you can take every single record and it's gonna give you an index. And what this allows you is that it's easy to distribute, right? So if you have like, trying to like simplify what I'm saying, but if you have like 3 different computers and you send like 3 different files to each one of those computers, they don't need to know what other computer is doing in order for you to get a result of the data. So all it needs is basically a latitude and longitude and the resolution that you need, and you will get the index. And then you can basically reduce that data in any other way that you need. We're using S3 for storing the data and also for receiving the data. So the partners that provide data to us, they drop all the data in the buckets and then we can use it. We're using DynamoDB, and this is directly from the our DynamoDB is called directly by the Lambda function on the site. And that returns some of the information that you see on the site, like how, like hours of operation and all the different stuff. We're using EC2 for mapping between different providers. So as I explained before, the 2 partners that give us the telemetry data is Betaset and XMode. And they were both really nice to work with, but they are actually competitors. So something that we wanted to make sure that we didn't do is that we didn't mix any of the data, and trying to make sure like we were not exposing any data that can be used by any of the companies. So all the data that we receive, we basically map into our own IDs. So that way, all the data is sort of like internal, and nobody else can try to use this data to map to something else. For the actual service that is rendering the data, we're using Matchbox. And to be honest, I didn't work a lot on the Matchbox side. The only thing that I did is that they provide an API. It's a Python API. It's quite easy to use. Like, you need just to define a few things, and then you can basically just send the data to them. Through this CLI, you can actually just ask to publish the data, and it's working. And finally, Amazon Lambda is basically just the endpoint between the site and our backend. So I mentioned before, like, so this project that we did is basically we're not monetizing this at all. In fact, everybody that works on this, and I have a slide here for everybody that worked on this project. Everybody that worked on this was basically volunteering their time, and sort of like was the agreement that TripAdvisor was not going to try to monetize this. And all the sponsors also provided either the data or the service or the computing power for free, with the condition also that we were not going to monetize the site. And we were able to do it with the collaboration of all of these companies as well. That's pretty much all. If you guys have any questions, I'm happy to take them.
We do have a question from the chat.
Yeah.
What's the smallest hex you can get from Lane Sadler?
What's the smallest what?
Hex? The smallest hex
Oh,
that you can get.
I think this is 19.
It's I actually dropped the link in the chat. It's about 18 inches on each side.
Oh, okay. So I was I wasn't referring to the actual like measure, but I think yeah, I think there is a. I remember saying this before. 18 inches. Well, that's really small. Oh, it goes so in H3 resolution, it goes up to 15. And this tells you actually how many unique indices are in the entire world when you use this. So it's quite a lot. For the project, we're actually using only 9 for businesses and 12 for open spaces, because we want smaller spaces so people can actually see something that looks quite nice for the heat map. But yeah, I honestly was really blown away by this project. Anybody using geodata, I will encourage you to look into H3 because it's quite powerful, and it has a really easy to use Python API. I mean, I never really worked with geodata before, and I was able to work with this quite easy, and sort of like installing it into all your workers when you're using Spark is also pretty easy. So you can actually use it.
Oh, excellent. Have you answered the questions from Sandeep? And we've got another from Payal. The Sandeep says, did you have to deal with raw GPS data from cell phone providers? I want to make sure this isn't the question. If so, how did you deal with the noisy data, especially in dense urban areas?
Yeah, well, dense urban areas is super challenging because so there are multiple things. One is a GPS accuracy. So one of the values that we had from the data set was how accurate the signal was. So we actually do an algorithm to try to see, depending on where it is, if the radius, if the accuracy is bigger than the contour of the business, we basically wouldn't use it. For most of them, it's around 5 meters, I believe. So it's usually pretty accurate, but we try to remove that kind of noise when the data is not that accurate. And the second thing that we didn't solve for is actual buildings. So if you go to New York, you probably see a building, like it's a residential building. And on the third floor, they actually have a business, like, you know, like a grocery store or something like that. So in one of them, we actually have the altitude, like of the signal, but it's super, super inaccurate. So we were not able to use that data to remove it from our data set.
All right. The next, it looks like for the moment, last question is from, I'm sorry for the name butchering, but Pale is, I might have missed this, but how do you decide on the best / optimal hex size to do your density analysis? Was it gauging by visuals or another method?
Sorry, can you repeat again the question?
I might have missed this, but how do you decide on the best / optimal hex size to your density analysis?
So yeah. So the answer to that is that, so I mentioned here that we had a bunch of volunteers. So we have some researchers that props to them, they did a really good job. And we have some people on design. And what they did was basically, we basically took only 1 day of data and we processed all this data with different resolutions. And they actually created like a study with different people inside TripAdvisor, because at that point we couldn't share anything with people, where they will ask them like what resolution was easier to actually detect, like when something was more crowded or not. And this was the sort of like user resolution 9 for data processing and 12 for heat maps was actually what looked the best. We did some testing with 13, but if you go in here like 13, it actually goes from 1.6, like, well, it's sort of like it's one like scale higher on the number of hexes that we will get, and the sort of like the value that we were getting from using like even like bigger resolution on the heat maps was not worth the cost. So once that you go into this, you start getting so much like data on those cross join that I mentioned, that it was like really, I mean, the entire process was taking much longer, and we were also spending a lot of the credits that AWS were giving us for this project.
All right, if that's it, Cesar, that looks like the final question. Well, do you have anything else to add to that?
No, I just want to say, if any of this seems really interesting and you want to go a little bit deeper, just let me know. I'm happy to, like help anybody a little bit with what I did. I'm not an expert on geodata, but spent a lot of hours like working on this project. So I'm super happy. I'm super glad to share sort of the knowledge that I got. And yeah, don't hesitate to reach out.
Wait, can I ask a question? Sorry, I was slow to the uptake here, but
yeah.
Just about your working with OpenStreetMaps data. So I've worked with that a little bit. Like, how do you like? Were there any like sort of lessons learned with like working with that? Because I know sometimes it's sparse and sometimes like iffy. I don't know if you like have any tips for working with that data.
So I guess the part with OpenStreetMaps that was the most challenging is that sometimes it contains polygons that are too big for us. So for instance, like the White Mountains in New Hampshire, right? So that's just massive. And we had to make like filter by area some of these polygons. And the other part that I actually didn't work on was actually extracting all the data from OpenStreetMaps. And I have a full presentation from the person that actually did it about how to do it. And I'm happy to share that as well. Well, it's not like a super detailed presentation, but I give you some idea about the step that he followed in order to extract all the data from OpenStreetMaps.
All right. It looks like we don't have any more questions. everyone's ready, I guess it's time to move on down the slides to Andrew's talk. All right.
Great, thanks. Let me share my screen. 1 second.
All right.
Does that look okay for everybody?
Yes, Andrew, it looks perfect.
Great. Well, I'll get started. So thanks, everybody. Really happy to be back and presenting in PyData Boston again. I'm going to be talking about a project that I worked on last fall. I was doing it for Bloomberg News as a consultant. Before we get started, just since I know the question would come up, unfortunately, I can't share the code to what I did here since this was a proprietary consulting project, but I'm happy to kind of talk through everything I did and answer any questions I can. I can share quite a bit, just can't share the code directly. So just to give a little bit of an introduction, my name is Andrew Therriault. I am a political scientist by training. I did my PhD at NYU. I've been working in data science for the past decade or so. I recently founded a company called Civin, which focuses on the intersection between innovative tech companies and governments and other public sector organizations who need their help. In the past, I've led data science and analytics teams at places like the Democratic National Committee, the City of Boston, and Facebook. I've taught at Harvard and Northeastern, and I'm actually one of the co-organizers of the PyData Boston chapter. So, as I mentioned, I'm talking about a project I did last fall for Bloomberg News. And this was in the run-up to the 2020 election. I built a series of machine learning models to predict voter turnout for them to use in their election coverage. And I'll explain the motivation in a minute. As we go, we'll walk through the project and talk about what the different challenges were and what I was thinking along the way. So just to give a brief outline, I'm going to start by talking about the specific problem this project was designed to solve. And then from there, I'm going to go into the general design of what my solution was. We'll talk for a while about the implementation and some of the challenges that came up through that. And then finally, we'll talk about how it actually went and what we can learn from the process. So first off, the problem of predicting voter turnout in a pandemic. I think I'll start by talking about what normally happens on election night. And pardon the interruption if you see or hear a corgi who is thinking, why am I on a call during her playtime? But we'll try to power through here. So on election night, generally what happens is that local election officials tally votes at the precinct level and report their results up to the counties and states. And then these results go to the Associated Press or another organization, and they publish these combined tallies. That's where if you go to the New York Times or Washington Post or wherever to see election results coming in, they're all sharing some of these same sources. And the key metric for tracking how much of the vote has been counted is what's called precincts reported. Basically, what will happen is that, of all these individual election precincts that report results, we know the total number of precincts there are, and we know how many of them have called in their results. So we can basically just use that proportion as a proxy for what percentage of the vote has been counted. And, this is an approximation. It's not perfect. For one, these precincts aren't all the same size. So, 1% of precincts, it doesn't actually mean 1% of votes, but it's close enough. It's a good enough approximation. Likewise, early and absentee votes, they're often counted and reported differently from election day results. Different cities and counties and states handle these things and others differently. Some might, for example, count your absentee votes at your local precinct. Others might count them at some central county election office. And what's more too is the order in which these are reported is not random. So for example, places with higher turnout, oftentimes in urban areas, they'll tend to report later, whereas the places with relatively few voters can do their counts pretty quickly. All that said, though, in a normal election year, the percent of precincts reporting tends to be a pretty good approximation of how much of the vote's been counted. So this is what it looks like in practice. And as a former DNC official, we're sort of revisiting some of my 2016 trauma here, but bear with me. This is from the New York Times website, from their election coverage in 2016. And so you can see here, I pulled up the Denver results specifically. It shows 346 out of 346 precincts reporting across the state. It says 100% reporting. That's simply based on that precincts reported number. This is what it looks like in a normal year. And that gives you a good sense of how many votes are actually in compared to how many there are going to be. So the problem with 2020. The biggest one that came up, well, obviously there were a lot of problems with 2020, but the biggest one that came up in terms of vote counting is that almost 2/3 of the votes were actually cast before Election Day. The previous high was about 1/3 in the last presidential election. And more than 1/3 of the total votes were cast by mail. And so part of the problem here is that, I mentioned a few minutes ago that those votes often aren't counted at the same time as the in-person votes on Election Day, and sometimes not in the same places, not at the precinct level. What also often happens is that these are processed afterwards. In some states, for example, this came up in Pennsylvania, early votes aren't allowed to be counted until the polls are already closed. So what might happen is that, you would get, say, voting machines results almost instantaneously after the polling closes, but you actually would have to open all of these envelopes and then process the paper absentee ballots one at a time. So those can take a lot longer. We saw, during, well, not election night, election week last year, that Pennsylvania actually took all the way to, the weekend in order to be able to get all of those votes counted. Also, one of the problems that we ran into was that the votes didn't even have to be in to the state or county by Election Day in many places. That in a lot of cases, when the rules were relaxed to allow easier vote by mail, one of the things that often got moved was the requirement that votes arrive by Election Day. In a lot of places, what happened instead was the votes had to be postmarked by Election Day. So that meant votes might come in even 4, 5, 6 days later. I think some of them as much as a week or two, they could come in. And so when 2/3 of the votes aren't being cast in the normal way on Election Day at polling places, suddenly that precinct's reporting estimate isn't really a reliable indicator of how much has been counted. So I got a call from Bloomberg News to help them try to fix this problem for their election night coverage. So the Associated Press had, told its members that they were going to be putting out these overall turnout predictions for every state. But they hadn't said, how these are going to be done. And they weren't making any promises about doing it at the county level or for congressional districts or for any race other than the presidential election. So that's what Bloomberg News reached out to me for. They knew me from reputation, from my past work with the DNC and elsewhere. And so, I agreed with them to put together predictions for each state, for each county, for each congressional district in the case of congressional races, and for presidential, Senate, House, and gubernatorial races. So these would be what Bloomberg News used on election night in their coverage instead of the precincts reporting measure. So to do this, I designed a voter turnout forecast model. And before we get to the details of the model, I think it's worth pointing out that making a model like this has some fundamental problems that you need to wrestle with. The biggest one, more than anything else, is that an election is a one-time event. That, yes, we have presidential elections every 4 years, but they're not the same thing. There are different candidates, different contexts. Last year there was a pandemic. These kinds of things happen. And so what often happens here is that, we try to proxy by looking at previous elections as a baseline, but it's not the same thing. So particularly in a year where it's just a fundamentally different environment than any that's come before, it gets really hard to come up with an accurate prediction. And what's more, contrary to what 538, The Economist, and other predictions might tell you, you can't actually quantify the uncertainty of a one-time event. I mean, this is a sort of a philosophical question, but it's impossible because you can't, if something happens, right? If an event happens, all you know about the probability of that event happening is that it wasn't 0. That's all you can say. You can't say whether the probability of that event happening was 100% or 0.0001%. We just happened to get to that one. It's really impossible to say when you only have one observation. So you can try to estimate it from other similar events, but that's not the same thing. And likewise, the other problem that you run into by using those past events that are similar is that you're relying on having comparable data and that the data generating mechanisms that produce that are comparable. So for example, just as a starting point, yes, we've had, over 50 presidential elections in this country, but we don't have all the same data going back that far. In fact, just getting county level presidential election returns, you can only do that for the past 20 years. And other data sources, for example, the American Community Survey, basically what the Census Bureau produces in years that aren't divisible by 10 to say how many people there are and what their demographics are and so forth. That doesn't go back to 2000. Its current format, it changes a little bit from year to year, but the current format of the ACS really only goes back about a decade. Likewise, the district boundaries for congressional districts, even the counties in the country, they do change over time. So again, it's really hard to get comparable data that lines up. And then when you're talking about rules, things like, who's eligible to vote absentee, how much early voting there is. Certain states now do all vote by mail, where that's a rapidly growing thing, but that wasn't the case 20 years ago. So you have to account for all of these things, and it's really hard to get all of the data line up. And then finally, like I said, 2020 was a very unusual year for many reasons. And so, expecting the patterns you saw in previous elections to hold is a bit of a challenge. So my goal here wasn't to come up with a perfect solution. It's one that was good enough. And this is sort of a philosophical approach I have about these kinds of projects, that I'm not going for a perfect solution. I'm going for a solution that's better than whatever it is we'd have if I didn't do the work. So in this case, maybe that solution is the AP's forecast, which doesn't get at the level of granularity we want. Or, it's going to be something that 538 produces or somebody else, or maybe they're just going to look at, the last election results and say, well, it'll be something more than that, most likely. In any case, I thought, well, I can't do better, or I can't do a perfect thing, but I can do better than those. So it's actually really freeing to think about it that way, to realize that, you're never going to have a perfect solution, but you can always make it better. And so that's my approach, to essentially start with some kind of baseline. In this case, I took simply the turnout rates we saw in each county and state from previous elections. And then, I thought, what can I add to that to make it more accurate over time? So one thing to remember here too is that data is always going to be messy, and this very much was. I'll get into that in a minute. But perhaps most importantly of any of these things, I think it's also really critical to be honest with yourself and with everybody else about what you don't know or what you can't know, and plan to work around that. So translating all these philosophical approaches into practical ideas for this project, first off, I had to really make some trade-offs about the amount of data I could use versus how accurate that was. So for example, I ended up only going back to 2004 with presidential results. I could have actually gone back to the 1970s if I wanted to use state level. But that only gives us about 50 data points a year rather than 3,000 like we get with counties. And I had to leave 2000 out only because basically we're using the lagged turnout rate from the previous election as one of the inputs. So we didn't have that for 96, which meant we couldn't use 2000 for training. We also had to, think about where is this data going to be accurate. So for example, I mentioned the American Community Survey a few minutes ago as something that in its current form only goes back about a decade. Well, I went back about 2 decades in the election results, and what that meant was I had to do a combination of different kinds of adjustments really to come up with estimates for the 2008 and 2004 numbers, where essentially I'm just did a really simple trend model from the data that I had for 2012 and 2016 and 2020. And those kind of things, come up along the way, and you have to make some really tough decisions about when to make those compromises and when not. As I went through, the other thing I needed to do was to, find a way to approximate uncertainty, even if you can't actually quantify it exactly, for the reasons I mentioned in the last slide. You can at least try to approximate it by testing it out on other elections. So in this case, I actually made 4 sets of validation models, one holding out each of the 4 presidential years that I was modeling, and use that to get a rough sense of how much uncertainty I should expect. But the biggest thing I did here actually is to recognize that, the things that cause variation in turnout rates across counties or across states, those are things I can estimate uncertainty around using past year's data fairly well. I can at least say, this is probably going to be right plus or minus 5%, 80 or 90% of the time. What's much harder is to say, hey, here is how 2020 is going to be different than 2016 or 2012 or 2008. And that overall level of turnout, we knew it was very likely to be high, but it was really hard to say how high. And so as I'll talk about a little further on, we actually ended up making 3 different sets of forecasts based on 3 different turnout level scenarios. And the idea was that on election night, we could actually use the incoming data that we were getting from the states and counties to say at what point should we switch from one forecast to another. So the final design of the model that I created, the most important model was the model of the county level presidential turnout rates. So looking at the number of votes as a function of the citizen voting age population. And so the inputs to this, I mentioned already, turnout in previous midterm and presidential elections. I also brought in a lot of information about voting rules, things like voter ID and whether felons are disenfranchised and so forth. There's a whole set of different demographics that are relevant here. And, a lot of this is based actually on the work that I'd done back in my academic days, studying what are the things that predict whether individual voters are likely to turn out. And then I also brought in a lot of information about the competitiveness of the presidential race in each state and about races for Senate and governor as well. Again, under the pretty well-established finding that the more competitive a specific race, the more people are likely to turn out. There's a second set of models as well about what's called down ballot drop-off. This is when people show up, they'll cast a vote for president, but they won't vote for Senate or governor or House of Representatives. They'll only vote at the top of the ticket. And so I made a second set of models predicting this drop-off as a function of the competitiveness of those down ballot races, a few voting rules, and socioeconomic status. Again, things that are established in the political science research as pretty strong predictors of behavior. So I mentioned earlier that I validated these models by holding out 1 year's elections at a time. And then finally, what I did was I retrained the models on all 4 elections and predicted for the 2020 context, and then made the adjustments to produce those high and historic level forecasts that I alluded to in the previous slide. And I'll get into a little more detail about those as we go on. So now a bit about the implementation. So probably half the work on this project was really just about finding and compiling the right data. So, one of the main data sources that I started from was election result data that was compiled at MIT, which has the most comprehensive and granular election result data. And, in this data, this was the data set that we could get county data for presidential elections going back to 2000. You could also get state data for Senate and gubernatorial races, congressional district level data for congressional races. What I found with this is it's generally very comprehensive, very high quality. But that said, there are issues in there. I found, for example, in some cases, the definitions of counties didn't line up because certain results were reported, for example, in Virginia, where they often would have a sort of joint county where they have a city and the area around it. They're technically different counties, but they report their election results together. Those kind of things came up. I found a few just basic math errors that I don't know where they came from, but the numbers were just off. Thankfully, I did some validation that helped me find hopefully most of those. But there were some cases too where I had to dig into places like Ballotpedia and Wikipedia to try to pull out some other sources of information. I mentioned the demographic data from the American Community Survey. The Census Bureau also puts out the Current Population Survey, which provides some similar data at different levels and frequencies. I pulled competitiveness from a bunch of different sources. The more recent stuff, it's pretty easy to get from places like 538 with all their polling archives. Ballotpedia is really good at compiling data on race competitiveness rankings from a few different sort of mainstream sources like the Cook Political Report. That's a pretty standard one that goes back a while. That said, though, those data sources generally start out around 2012 or so. That's when those organizations started compiling that. Prior to that, I actually had to go and do things like look up old newspaper articles from, say, 2000 or 2004 or whatever, to try to find, what, for example, the Cook ratings were back in 2004, because they're not available online anywhere. Those sorts of things I had to go back and dig around to find. Likewise, I also had to go to a lot of different sources to get information about voting rules. Again, this is one of those things where it's not too hard to get current data, but when you start trying to roll back in time, that's where it gets tough. I had to go and research and say, for example, when did a certain state start requiring voter ID, so that I can code, the elections before then as not requiring it, but the elections afterwards as requiring it. Because that's one of the things that we're thinking about in terms of what predicts overall turnout rates. It's not only what the rules are now, but what they were at the time of a previous election, and even how they had changed in the run-up to that election. So all that's to say, getting data that's consistent across years was a real struggle. And one of the things that I wrestled with is the subjectivity in deciding when data is good enough and when it's not. I feel like if you had 100 people do this project, you would have 100 very different projects, because I think everybody will have different views about how to make these trade-offs. And there's no one right or wrong answer. There's no standard for how to do this. Ultimately, this is the sort of art and science of this kind of project. So I did most of this work in Jupyter. I think a lot of you are familiar with Jupyter notebooks. And if you're really a big fan of Jupyter workflows, I did a JupyterCon presentation a few years back on using Jupyter notebooks in production and kind of how I approach that. But just to really kind of summarize how I do a lot of projects normally, the way I start, and I'm speaking as really a data scientist, not an engineer. So, I'm sure a lot of software engineers would cringe at what I do. At the other end of the spectrum, I think a lot of researcher types wouldn't get past the V0.1, so I'm okay with being in the middle there. But so what I start out doing is doing everything in linear code. I do things one at a time in either one or many notebooks. And then the next step of what I'll do is I'll take things that generalize, particularly around things like building models. I'll move them into functions within the notebook, and I'll start pulling out the parameters, put them, say, up at a block at the top of the notebook, so I can play around with them as needed without having to dig through all the code. The V0.3 is often moving those functions into modules and importing them. Basically, that's what I do once I get those functions in a place where I'm happy with them and don't need to make changes. The optional V04 is maybe I just move everything into a standard Python script. I mentioned that JupyterCon presentation a minute ago. I find this part to be more and more optional over time, because you can actually use notebooks in a production setting. If you're not familiar with something called NB convert, I would advise you to look into it if you're interested, because what it allows you to do is to schedule a notebook run where you don't actually have to be doing it manually. It can run on a cron job or an Airflow or whatever, and you can get all the same outputs you would as if you had it open in the browser. And then finally, I move everything to production. But so for this one, this was a sort of fast-paced project. I had about 6 weeks to put it together. I was also working alone, and this was something that hopefully I wouldn't have to do again anytime soon. So I went with a sort of hybrid approach, hybrid of 0.1 for the brand new code and 0.3 for things I've adapted from other projects. Like a lot of you, I'm sure, over time, I've realized I do a lot of the same things the same way, particularly when it comes to machine learning. So I've got a pretty well built out code base of how I do things like model tuning that I can just reuse for different projects. It wasn't the cleanest, most elegant approach. Like I said, a lot of software engineers might object. It worked great for me, and especially to needing to move quickly, I felt like that struck the right balance. That said, this is one that I was working alone on, and it wasn't something that I was going to need to replicate later. So if those are considerations, maybe try to be a little more deliberate in your workflow. So one thing I did a lot of in this was ensembling. So this is a common thing too when I'm making models. for those of you who aren't familiar with ensembling generally, the basic thinking is that every model has weaknesses, but by combining different algorithms, the idea is hopefully by averaging those predictions together, you can cancel out some of the weaknesses and build a model that's better than what you could get from any individual algorithm. So the final presidential turnout models we used, they used 3 different tree-based algorithms: random forests, extra trees, and gradient boosted decision trees. And the idea behind this was just that each of these algorithms handles the input features in a slightly different way. For example, random forest regressions, they tend to give more weight than extra trees regressions do to continuous features because of the way they select where to split, make splits within your data set. I could talk for hours about the logistics of that. Just suffice it to say that they tend to focus a little more on continuous variables, whereas extra trees models tend to go a little more towards the binary variables. And so the idea of combining them together is that you give different features a chance to shine in each model, so that none of them just happens to not really get much attention simply because the particular algorithm you used just really doesn't have much of a taste for that kind of feature. I also tried using linear regression and various kinds of regularization, but I found actually in the testing, they made the ensemble predictions worse. Tree models tend to be really flexible. Regression-based or linear regression-based models aren't very flexible. And so, you either have to build in a lot of interactions manually, or else you just have to accept that, interactions between the different inputs aren't going to be accounted for. And so that made the predictions substantially worse, and I ended up excluding them at the end. The one exception was for the down ballot models. In those cases, we had a much smaller sample. For the Senate and governor races, we were doing it at the state level, so only a couple hundred data points. And I apologize if you hear my dog squeaking her toy. She does this when I'm on Zoom sometimes. So we had a lot fewer data samples. We had fewer features and simpler specifications. So for those, I just used linear regression for simplicity. But for the much larger presidential turnout models, that's where we actually used all of the tree-based models. So there was a lot of tuning that went on in this. I spent a lot of time manually collecting and refining the data, but what that actually translated to in the modeling wasn't so much setting up the model that took time as figuring out, which algorithms to use, how to choose the right set of features to include. There was a lot of tuning and retraining. Also, when I went back and I would pull in, a slightly improved set of data after I did some error checking and so forth. And the basic setup here of, what went into this, just the presidential models, we had about a little over 3,000 counties, 4 years of data, depending on the run, anywhere from 50 to 100 features, 3 to 5 algorithms at a time. We were tuning 3 to 5 hyperparameters per algorithm. We were doing 4 validations sets of models plus the final set of models. All that, those numbers don't really mean much other than to say there was a lot of horsepower that we had to use to compute this. And the laptop I got a few years ago, it was meant so I could put in a bag back when we used to leave the house and go work in other places, and it's great for that. It's not that powerful though. And so the solution I found was actually to use a tool called Dask. So if you're not familiar with Dask, Dask is a Python library that basically allows you to distribute data tasks across different workers. And in particular, where it shines is doing it when you're distributing across a cluster on more than one machine. You could also use it for parallelizing things on a single machine. It's a good use case for that, but in this case, deploying on a cluster was really what I was going for. And I used a product called Coiled. Coiled is a company that was started by the creators of Dask. And they have a product called Coiled Cloud, which is essentially a Dask cluster as a service on AWS. So Dask, when you're using it for this use case, it's basically a drop-in replacement for JobLib in scikit-learn. JobLib allows you to parallelize a job, like in this case, a randomized parameter search. JobLib lets you do that on one machine. Dask lets you do it either on one machine or on a cluster. And so switching to the Dask backend was actually really simple. It was less than 10 lines of code, took me under an hour, the exception of a little debugging I had to do, just basically because it's the first time I'd done it, and I actually work on Windows, unlike most people. And so there are a few nuances about it, but it was pretty quick to do. And I've since used it on other projects, and it's literally no more work than using scikit-learn on its own. And the beautiful thing here is that Coiled, because it's still in beta, is actually free at this point. It still is. There's a link here. If this is your thing, I definitely recommend trying it. Was really happy with how it turned out. Because I was able to use up to 200 cores on their cluster. And so I set up a cluster of 48 machines, each of which was as powerful or more powerful than my laptop. So you can imagine what that did to the time it took to run everything. So this is just a screenshot I grabbed at the time. This is their monitoring system. In this case, this was one round of hyperparameter tuning for, it looks like an extra trees model. What it's showing here is all, I think, 48 jobs running. The whole thing to do this took about 2.5 minutes, it looks like. That's the kind of thing that before I switched over was about an hour or two to run locally. And so that really sped up the iteration time. So then what I did is I mentioned validating the models where I held out 1 year each. And so there were two purposes for this. One was just to make sure that the models actually worked as intended and that, I was able to produce useful forecasts. But more importantly, I also wanted to get a good sense of what the uncertainty in the predictions was likely to be when I made a model of other years than the one I was testing in. So basically, this allowed us to look both, how much variance do we expect to see in our predictions across counties or across states, but also overall, and because that's the really hard thing, and the hard thing that I was worried a lot about when it came to 2020. How do those year-by-year patterns change? So on that last point, looking at the 4 different years, basically it ranged from our predictions being about 3.5% too low in 2004 to 6.3% too high in 2012, which kind of makes sense. For example, the 2012 one in particular, 2008 was a really high turnout year compared to some of the previous ones. In 2012, we did see turnout drop pretty substantially from 2008. So remember I mentioned that the past elections turnout was one of the big inputs. Well, it makes sense then that if that's our starting point and turnout goes down pretty substantially, that we are going to see our forecast coming in a bit high. So then going down to look at the more granular level, this is where I really wanted to just get a sense of how close were we overall. So there are always going to be outliers when you do these things. And I looked a lot at the outliers to see, were there particular patterns that were coming up, places, for example, one of the things that I did as a result of doing some of that outlier checking was to actually incorporate as a feature the growth rate of the population in a certain area. Because what I was finding was that there were some places that were rapidly growing or shrinking where it seemed the census estimates actually weren't keeping up with the change in population, in part because we only had census data from 2 years prior, because for 2020, the last estimates we had were 2018. So we had to do the same thing in previous years to use the lag data. But also, this was something I did to find some errors in the data, look and see where our forecasts were way off. And, in a number of cases, we were able to find, oh, that result is just fundamentally wrong. So it was really useful for that purpose. But, mostly I wanted to say, well, we know outliers are going to happen. What I want to make sure is we get it within a reasonable range most of the time. So I looked at the 10th and 90th percentiles. And, going in both directions, we were within about 6 percentage points. Either 5.3% too low at the 10th percentile or 6% too high at the 90th. And for the median county, we were plus or minus about 3% of what the actual result was. So overall, my takeaway here was, this is pretty good. We're not dead on, and I never expected to be. Like I said, my goal was a good enough solution. But I thought this was pretty solid. And this was something that, I figured is going to provide a pretty useful forecast. So just to illustrate what this looked like, so, I did the numeric summarization on the previous page. These are some of the graphs I produced. This is for validations for 2004 and 2008, those being the holdout years. You can see on the horizontal axis, the predicted turnout rate, and then on the vertical axis, the actual turnout rate. And the dots here are scaled by the size of the county. You can see that particularly when you see the extreme outliers, a lot of them tend to be the really small dots because there's just a lot more variance around smaller places. But you see in both cases, we actually track really well. If you're looking at the R² of this, I don't have the exact numbers in front of me, but you can guess it's quite high. And so this was really reassuring to say, yes, the approach we're using here, there's some variance in terms of, or I should say, there's some bias in terms of, you can see, for example, in, I mentioned before that in 2004, we were about 3% too low on average. And you can see that because, the typical results, most of them are sort of above and to the left of the diagonal line. That means we were predicting too low. 2008, though, we were about dead on. There's very little bias in that year. So that was pretty reassuring. And that also gave us a good sense of, approximately what uncertainty we should expect. So getting ready to actually go live on election day. One of the things we decided to do was, rather than present a single estimate of how many votes we expect, instead we presented our forecast as a range. And we decided to go with plus or minus 5%. I mentioned before that the 10th and 90th percentiles we were seeing by county were, between -5 and +6. I said about plus minus 5%. That I figuring that should capture, definitely the majority of cases. Hopefully at least about 2/3, maybe 3/4. And that seemed like a pretty reasonable target. At the end of the day, though, this is kind of arbitrary. The goal here wasn't that this is any precise estimate of what we expect to see, and we didn't present it that way. We basically just said, look, we expect in most cases the result will fall within that range. And to give a bit of a spoiler, they did. It worked out. One important thing we did here was actually applied the same range at all levels. So this is something that really gets to the structure of errors. And for me, this is particularly important because when you see something like a polling forecast, what oftentimes polling forecasts rely on, and this was one of the big problems in 2016, why so many forecasts got it wrong, is they assume that, by averaging different polls together, the errors will kind of cancel each other out. And you won't have what are called correlated errors, which is that, all the polls may be wrong in the same direction. By applying the same range at the county level, the state level, and the national level, what we said was basically that, we're saying the same uncertainty level at all levels, meaning that we might be, wrong in the same direction every time, and that's okay. We'll still, we're not going to assume these things are just going to cancel out. But the other thing we did too is, I mentioned before that we calculated 3 different types of forecasts based on 3 different levels of turnout. So our baseline forecast was just on our model's predictions. So what that said was, let's take, the average of the trends we saw across the past 4 elections, not just average the turnout levels, but the sort of turnout patterns generally, and adjust them by changes in, for example, the rules around voting. So, when there's more absentee and early voting, that tends to increase turnout rates. So we did allow for that. And so, we were looking at an increase in the turnout rate over the average of the past 4 cycles, but, a fairly modest one. But, that said, we were looking at the number, I believe it was something like 142 million, our baseline turnout forecast. And, this was lower than, well, pretty much everybody else's forecasts. It was also just lower than we realistically expected. There were a lot of different signs of enthusiasm we were seeing among the electorate that we couldn't ultimately incorporate. One of the things that often comes up is in surveys, people will ask about how excited people are to vote. Generally, the question about asking people, do they plan to vote? It's actually not a great question, but other measures of enthusiasm can be fairly predictive, at least to tell one election from the next. But again, this is one of those problems where we didn't have consistent data going back to all the previous elections, so we couldn't account for that. So, this was a case where we were seeing things in the data, but we couldn't put it in the model because we didn't have data from previous years that was comparable. Just for comparison, like the 538 forecast, they had their sort of magic formula of how they generated turnout forecasts. And they simply said, hey, we think, enthusiasm is, I don't know, 20%, I'm just making this up, but 20% higher than it was last time. And so we're going to make an adjustment. But, as far as I could tell, totally arbitrary what that was set at. And so I didn't want to do something like that. Instead, what we did was say, well, we don't know how high turnout is going to be, but, we think that the baseline model, the model from our turnout forecast based on previous years, let's say that's the low end. So high turnout, we said, is going to be about 5% higher. And, that 5% figure, we basically just looked at the variance across previous elections. So 5% is basically about the same as the difference in turnout rates between 2004 and 2008, those examples I showed you earlier. And, generally 2008 was a pretty high turnout election going back, the past several decades. So we said, okay, the difference between a high turnout election and a normal one, it's roughly 5%. Again, this is kind of arbitrary because at the end of the day, this isn't something where we can estimate precisely, so we're not even going to try. Instead, we said, looking at the data, that seems like the difference based on historical patterns between a normal election and a high turnout one. But then looking at this year, or at 2020, there were a lot of signs that it was actually going to be more than that. In particular, looking at the rate of early and absentee voting, I showed earlier that we had over 100 million votes cast before Election Day, and that's more than double we'd ever seen in the past. And obviously, a lot of those voters were people who otherwise would have turned out on Election Day. But still, that was a really strong sign. The enthusiasm was very high. Likewise, all the other signs, pointed the same direction. So we also decided to come up with this historic forecast, which simply takes the high turnout forecast, adds another 5% to it, and decided essentially that we're going to, start with the baseline forecast and then move from one to the next throughout election night based on the data that comes in. And finally, the other thing we did before we released was we wrote up a pretty extensive methodology document and published it for everybody to see. So, one of the things we were trying to do here was to be really transparent about what we were doing, what the inputs were, give some sense of what the uncertainty all meant. This is a pretty complex project, and I wanted to make sure that while I wasn't going to get to the level of, making it totally academic, I wanted to make it so that a sophisticated reader would get a good sense of what they were looking at. So finally, the last section before we wrap up, what happened? So on election night, the plan was, we're going to load up our baseline forecast. And for each, as I said before, for each state and county, we'll be showing a range of the total votes we expect. And so the plan was that, we have these high and historic turnout forecasts. And what we did is we set some conditions for when we're going to switch from one to the other. And that's based on a certain number of counties or a certain number of states crossing the upper bound of the range of whatever turnout forecast we're using right now. We presumed we're only going to go up from the baseline. We did set some conditions for when we might roll back, but we didn't expect to have to use that. And then on the site itself, what it would show is the counting progress for votes as a percentage of the expected number of votes under the forecast. That is, it ends up becoming a range of percentages, as I'll show in a minute. And we also make a point of explaining which forecast we're using at any given time. That's why, if you looked at one point in time and saw, oh, we were, somewhere between, say, 80 and 90% of the votes counted, and then suddenly you looked again and it said 75 to 85, the reason would be, if you looked at it, that, oh, we've switched from one forecast to another. So first off, the national tracker. This is what was on the front page of the site. It had, like you've seen in a lot of places, it'll have all the states. You can mouse over it and pull up the state specific info. They also had a tracker to look at the progress of counting votes overall, and to look at the sort of partisan composition within each of those. They also did some cool things around, those lines on the right. The reason the colors change over the course of it is so that they can kind of track the progress of votes that come in. So for example, if you look at, say, Nevada, it started out very red because Clark County, which is where Las Vegas is, the really blue part of the state, that counted more slowly than the more rural parts. And so the votes that came in late were much more democratic than the early ones. Anyways, you can kind of get a sense here too. These aren't the final results. This stopped updating before every state had finalized its vote counting, but this is close to it. You can kind of get a sense just looking at this, how close we were to the 100% of the forecast. And this is, I'll mention in a minute, I'll get into this in a minute. This is the historic turnout forecast, which we got to very late on election night. But you'll see, on average, we were just about in the right territory. There were some places that were a little high or a little low. Overall, it worked out pretty well. And when you looked at individual states, here's Georgia, for example, the way you would see it is, they would show the results and the number of votes counted, but then again, show, how many votes have been counted, and then what the range of expected votes here is. So in this case, in Georgia, there were 5 million votes in total. The range of this historic voter turnout forecast was 4.78 to 5.28 million, which means, the mean of that is 5.03. So we were dead on in Georgia. Unfortunately, we were really close in a lot of places, particularly places that turned out to be really close. The problem with Florida. I kind of laughed when I wrote this because I could come up with many issues to take up with Florida, but in this case, it's not Florida's fault. They actually did something right, which was they reported their vote counts super early. And it was really frustrating because what was happening was there was super high turnout in Florida, and they actually were one of the states that really overperformed relative to our forecasts. But by pretty early in the evening, around 9 p.m., most of the places were fully reporting. And at that point in the night, no other state was anywhere close to as complete as they were, and they were getting a lot of attention, particularly because it came in much more Republican than expected. And so we were still on our baseline forecast, and we were seeing some counties coming in as 120% of our forecast or more. And so, the team that I was working with at Bloomberg Graphics, they were getting calls from the news desk saying, hey, why the hell is our forecast so far off? And then they were asking me, and I said, well, we have these rules and we're not there yet. And so we're really stressing out about this. We hadn't met the trigger for going to high. We did eventually just, later that evening, switch it up there. I don't know. I think we got close to the actual trigger. We might have even crossed it, but we at some point we just realized, yes, it's obviously going to get there. And in hindsight, we'd probably adjust the rules a little bit, but overall it worked. It was just a little slower than expected. We also switched to the historic forecast around 5 a.m. or so. I don't remember exactly when. It was sometime before dawn because I remember going to bed around the time the sun came up that morning, and then waking up a couple hours later and getting back online. But we made that switch. We ended up getting to that historic forecast, and ultimately I'm glad we did. Just to contrast the Florida example though, the problem with New York, as their own folks say, this is City and State, which is one of the New York political magazines, they described it as a national embarrassment because even weeks after the votes were cast in New York, they still hadn't finished counting. They even managed to miss legal deadlines to do so. And this was true for several states. So that's why, when you look at the site as it is now, it's actually showing that we only got to about 96% of the forecast in nationally. And that's because, then when they stopped it about a month after the election, not all the votes were in places like New York were actually still reporting. So overall, we're actually pretty much right on target. So the final vote count was just a little under 160 million. Our forecast was 161. The range was 157 to 165. So, we were within basically a percentage point of the actual turnout number. That's our historic forecast. That's because we were able to adjust with time. But that was the point, it worked as expected. And what I think was really pleasing to me was that in a lot of key swing states, our forecast was similarly dead on. So, places like Georgia, Michigan, Nevada, North Carolina, we were within 1%. A couple places like Pennsylvania, Wisconsin, we were a couple points off, but not far. We did see some places where we were off by quite a bit. Places like Hawaii and Idaho. But that said, and this was kind of my focus. I didn't do anything with waiting to do this, but I definitely made a point of, really focusing on the data checking on places that I expected to be swing states. If I saw a potential data issue in Idaho, I wasn't going to waste a lot of time trying to fix it. But if it was Wisconsin, I absolutely was. But likewise, I think a lot of this has to do with turnout being more consistent in places that are highly competitive. So at the end of the day, everything was within plus or minus 7% of the historic forecast, and most places were within plus or minus 5%. So, that's what we were hoping for, and that's what we got. All right, so finally, I was really pleased with how this worked out. 2020 was a hellish nightmare of a year in a lot of ways. And I was very pleasantly surprised to see that this one thing actually went as well as I could have expected. But the real credit, doesn't go towards some brilliant design or magic. It was humility. The humility of presenting forecasts as ranges. So you set the expectation for the audience that you're not going to be exactly right every time. And this is one of the mistakes I think that places like 538 have made. In 2016, for example, they got a lot of heat, as did pretty much everybody else who was aggregating polls, for missing the election because they were off by a couple points. That was partly the fault of what I mentioned about those correlated errors, where you're getting a little too cocky that everything's just going to even out when you aggregate all this information together. And so in our case, we presented these ranges to set the expectation clearly that, yeah, we're probably going to be off by a few points here and there, but that's okay. That's just the plan. Likewise, we didn't assume that those errors were going to average out. We presented, as much uncertainty at the national level as we did for counties. And then we designed the system knowing that it was impossible to know everything in advance, that 2020 was going to surprise us. And so rather than either pretend it wasn't or to throw up our hands, what we said was, let's design a system that allows us to adapt to the data that's coming in a really basic way. It wasn't something like, the New York Times needle or what Washington Post did at the very end, where they tried to come up with some dynamic forecasts. Remember the Washington Post, they didn't turn it on till like 2 days later, because it turns out, those models are really hard, and I've done that before. I did that at the DNC in 2014. I had no wish to ever do that again. Instead, we did something really simple, which is let's come up with a low, medium, and high forecast and switch from one to the other based on the totality of the results that are coming in. And so that actually ended up being a very simple, but very effective solution to get to the answer we needed, which was how many votes are going to be cast. At the end of the day, we got there and we answered the question we needed to. That said, definitely room for improvement. One thing I would do differently is pay more attention up front to data quality. And part of that might mean scaling back my ambitions about what data I was going to include. I think particularly a lot of the things about voting rules, I kind of felt like, well, we need all the information about voter ID and felon disenfranchisement and how many days of early voting there are in every state, in every election. And, ultimately, when I actually ended up running the models, most of those didn't prove that valuable anyways, but it was a hell of a lot of work, and it could have introduced as much noise as it took away. I don't know. But I think for the sake of doing this more efficiently in the future, I think, paying attention to the data that we know is quality would probably be a better approach. In terms of the adaptive forecast, I mentioned the problem with Florida and moving from one level of turnout to another. I think in the future, I'd be a bit more willing to take risks on that. The problem we ran into with Florida was we didn't have a mechanism to just say, hey, there's one place that we think is a good indicator of where everything's going, so we're going to move the national forecast based on that. You know, and in hindsight, if I were doing it again, I'd either make the rules a lot more loose as to when we do that, or maybe, you know, do it on, say, a state-by-state basis. So we could have, say, flipped Florida to the historic forecast early on in the night, rather than have to wait and kind of look silly for a little while. And then finally, the other thing I do when I was going through this and thinking about, you know, sort of my philosophy of approaching these projects, I realized I did one thing that really goes against the way that I like to do it and the way I actually teach my students how to do it. Because one thing I always like to remind my students is that you can always add complexity later. It's much harder to take it away. And I think I violated that when I did this project. I came up with this really long list of all the things I thought it should be included. And I kind of started from there, and I took a few out along the way once I realized, say, that I couldn't get some data set that I needed. But in hindsight, you know, if I were to do it again, I'd probably go the other way, and I would start building up more gradually, because it's really unclear to me how much of that complexity was really necessary. I mentioned things like voting rules, where at the end of the day, the features actually didn't add a whole lot of value. And I think that's probably the case for a lot of things. For example, you know, I mean, I was able to look and see, hey, for example, you know, adding additional algorithms to the ensembles, you know, yeah, they improved overall performance in terms of my sort of key metrics. But I didn't really dive in and see, like, is this a meaningful difference? And is this slight, you know, improvement in R squared or whatever metric I was using, you know, is that really worth the added complexity of having multiple algorithms and having to retune everything? You know, in hindsight, maybe I'd go back and try it a little more simply, see how well that performs, and then only add complexity if it actually makes the model notably better in a really substantial way. So that's all I've got. I've got a few minutes if anybody has any questions. I think I saw some pop up in the chat. You can always find me on Twitter. I'm very easy to find there, and you'll find lots of corgi photos and burritos, as well as snarky comments about tech. You can also shoot me an email here, and I've posted the slides on my GitHub. I did that right before this. So if you want a copy, just go there and grab them. You know, and feel free to share or send me an email if you have any questions. With that, yeah, I'll take a few questions from the chat.
All right, there are a few. Lane would like to know, have you compared Coiled to Saturn Cloud?
No, I haven't. Not familiar with Saturn. Definitely, actually, I'm going to write that down because I'm curious.
All right, next one is from Cesar. Can you explain a bit more about how the actual data was fed into the model and the predicted data was read out of the model on election night?
Yeah, so we actually did this. So I tried to keep it as simple as possible. And you know, I mentioned back in 2014 that I was doing election forecasting for the DNC. This was basically a team of 5 of my data scientists in a room at Democratic Party headquarters, and then a couple dozen people around the country who worked for different firms and state parties, and everybody kind of gathered together and entering data and then rerunning models. And the lesson that I took from that was I never want to do anything like that again. And so for this one, I actually kept it really simple. So, you know, I brought in the data manually, you know, literally grabbed it from whatever site I could and saved it. There were some cases like the census data where I did use the API and I just had a script where I went and pulled it, but I wasn't doing that dynamically. I wasn't doing that at the time of model training. I just wrote a script to call it, prep the data. So I, you know, got that done weeks in advance. And then on the output side, again, I kept it as simple as possible. You know, the Bloomberg folks, they had their back end for the application they were using, but all I did is I delivered them a giant CSV, or actually I guess 3. I gave them I think I gave them a national forecast, sorry, 3. There was a state forecast, a congressional district forecast, and county forecast. And all of them were CSVs. And then, you know, every data point for that forecast was a separate column. So there was a column for the, you know, upper and lower bounds of each of the forecasts, as well as the midpoint. And I gave that to them 4 days in advance. They got it loaded. And so on election night, when we were switching from one forecast to the other, literally all I had to do was send an email that said, hey, switch to the high forecast. And then somebody on the application team just repointed to a different column.
Okay, that last question was actually from Brent. Andrew, Cesar's real question was, Andrew, did you consider using campaign advertising spend on the models?
Yes. Definitely something I was looking into. This kind of gets to that question of comparable data from year over year. And this is one where I really struggled. This was, if I had, so I originally spec'd out this project around the beginning of August, but the contract didn't come through till the end of September. But this was actually one of the data sources that I had originally envisioned, was FEC, Federal Election Commission data on campaign spending. I probably wouldn't have looked specifically at advertising. Rather, I think overall spending would have been a fine proxy. I think there's a few problems with that, though. Is one, from year to year, you get a lot of variation in cost. And it's also a very nonlinear thing, so it's a little tough to figure out how to model that. There's also just a lot of complexities around things like media markets. So, depending on whether you're, say for a congressional district, if you're in an urban district versus a rural one, your ad buying costs are going to be totally different. Like if you're running, for example, if you're running in upstate New York for a congressional seat, you're going to be blanketing the airwaves with TV ads. If you're running in, New York City, you're probably not running any TV ads because you're sharing that market with 20 or 30 or 40 other congressional districts. So it really dilutes the impact. So it's a bit tough. Also, the other part is simply that, that would be a lot of data to wrangle. FEC filings are notoriously hard to work with. And, there's certainly data sets that have been put together by others for previous elections, but I'd still have to go and do that for, the present year. And part of the problem too was, a lot of those reports only go through, for example, if I was doing this in October, I would get the report through September 30th. And for all of the previous years, I'd have to go back and recalculate those with respect to the same date on the previous cycles. So at the end of the day, it's just one of those things. It could have been done, but that was a choice I definitely made for the sake of reducing complexity rather than adding it.
All right, thank you. We have another question from Tyler, potentially a bit speculative, but are there any data sources that you think will grow importance if the mail-in voting trend continues or goes digital post-pandemic? Are there any data sources that don't exist that would improve the model, specifically decrease variability?
Yeah, so mail-in voting is actually really, really helpful for this in general, in part because, well, there's a couple of things. One, people who vote by mail tend to be pretty consistent. And so, for example, if you're somebody who's voted by mail in the past, you are much more likely to do it in the future than if you say voted in person. That's less of a solid predictor. I think the big question is going to be whether the trend towards mail-in voting is a uniquely 2020 thing or if it becomes more permanent. Because places like Colorado, for example, that have switched over the past decade to all vote by mail, they've tended to see much more consistent high rates of turnout. The problem we had this year was not knowing how to account for the switch to mail-in voting. Excuse me. For the switch to high rates of mail-in voting because of the pandemic context. Excuse me. But the other thing I was thinking about with this is mail-in voting does give you two advantages when it comes to prediction. And again, I couldn't take advantage of it this year because we didn't have good precedent from previous years to know how much this was going to affect turnout. But one is that in order to vote by mail, you need to be registered ahead of time. One of the tough things for forecasting, good for turnout, bad for forecasting over the past couple of decades, is the move to same-day registration in more and more states, which is great because it removes a barrier to voting. But it's also tough because the number of registered voters is a less valuable signal than it used to be. because, back in the day where you had to register, say 30 days out, you at least knew what the denominator is on the total votes. And that's not something with same-day voting or same-day registration, because a lot of people might show up who aren't on the voter rolls at all that you don't know about. With voting by mail, you do have to be registered ahead of time. And so that does give you a useful signal, not only of the total number, but for any individual. One of the really helpful things about a voter registration is it can tell you, is this person currently located in this location? On an individual level, things like an updated voter registration is a really important signal. But then the other thing is, you also get mail-in ballot requests. And so, if I'm in most places, you can't just print out a ballot online and mail it in. You have to mail in an application, they send you a ballot, and then you send that back in. So we know who's requested and been sent a ballot already. And that's a really strong signal as well. And it can tell you both, for an individual, are they likely to vote, but also just what the level of enthusiasm is. I think the challenge in 2020 was, again, totally different context. And especially there were lots of states that were, there were some states that were mailing everybody an absentee ballot. There were others like Massachusetts where they didn't mail everybody a ballot, but they mailed every registered voter an application. And so they removed one of the barriers that you previously had. So because of that, requesting a ballot was no longer the same kind of signal that it was in previous years. So that was the kind of thing where, again, like some of the other competitiveness metrics, we were seeing signals that interest was high. The problem is we just didn't have enough precedent to say how that would translate to some change in probability of voting or change in the expected level of voting. And so I couldn't factor it into the model. That, again, is the kind of reason why we made that forecast that allowed us to jump up to the high in historic forecasts, because we knew that turnout was almost certainly going to be higher than our baseline prediction. We just didn't have a good way to say how much higher and how that might vary from place to place.
All right, excellent. We'll give the last question to Drew. Do you think this model could be used or adapted to detect voter suppression or intimidation?
I would be very, very concerned about that. And that was something I saw a lot of problems with on election night and in the aftermath, where a lot of the claims about voting irregularities often came about because people were looking at the AP's forecasts, which most news organizations were using, and saying, hey, why do we have too many votes or not enough votes? Like the numbers don't line up, without recognizing, and this is part of that problem with the black box model that I was trying to avoid with all the documentation. People were assuming that those were actual counts of ballots. And so that somehow the Biden plus Trump number didn't match the total count, and that there was something wrong there, when in fact, those are two separate things. And it was just simply that the predictions were off. And I would be really, really nervous to use this for things around voter suppression or intimidation, because you would need something happening at a massive scale, for it to be detectable. Because like I was saying with my model, I expect variation that's plus or minus 5% to happen, 10 or 20% of the time, at least. I expect variation that's, 7 or 8 or 10% off from the prediction to happen many places, not a lot of the time, but maybe 1% of the time, 2%. And those, so when those things are normal, you would need a massive effect of voter suppression or intimidation for it to be meaningful. So, if I see the model as wrong compared to the actual real world results, my takeaway isn't that there's a problem with the results. My takeaway is that, well, that's just the model being wrong. I think a lot of other data scientists, particularly in politics, are really bad at remembering to have that kind of humility. But my first take is always that, if the model and the actual real world data don't line up, more likely than not, that's the model's problem, not the real world data. So, in this case, I would be a little hesitant to try to use it for those circumstances. You could always use it as a way to start. And I think going back to that 2014 example, when I was at the DNC, we were using the election night incoming data compared to the forecast to look for signs of irregularities. In that case, for example, one that we were looking at, it was a county in Maryland where we thought they actually just had the numbers backwards between the Democrat and the Republican, because our forecast was like 60-40 and the results were coming back 40-60. Turns out that county just really hated our candidate. I still don't understand quite why, but like those numbers were right. We were just off by 20 points. And we had sent in the lawyers to literally inquire about this, the DNC's lawyers, which I think was a good use case, but I think it's also a great example of why, even when you see something as seemingly wrong as the numbers being off by 20 points, that happens, especially when you're looking across a large number of geographies. So I'd be really wary about using it for that use case.
All right. Do any of you or any of the organizers have anything else to add?
Not really. I just want to thank everybody for coming and thank everybody for staying. I know we've been going almost 2 hours and I see almost everybody is stuck around. So very excited to see that. And thanks to you as well and everybody else who helped organize this. Really great to have more people contributing.